After going through this module, you shall be able to know some general points about selection rules for IR and Raman spectroscopy. Learn a direct way of checking the activity of the vibrational modes. Learn a simple method of classification of vibrational modes in terms of internal coordinates. You will be able to explain the detailed procedure for getting vibrational modes by taking water molecule as an example. And we will be able now, or also we will learn how to assign the given spectral frequency to the various internal coordinates. You already know about the selection rules for IR and Raman vibrational spectroscopy. Also, you know about the IR and Raman activity of vibrational modes of water and POC3 molecule. In this module, we will learn little more about selection rules, and then classification of vibrational modes will be taken care. Now, some general point about selection rules and for IR and Raman spectroscopy. These are: number A, IR active modes can be distributed among only 3 symmetry spaces, and Raman active bands can be distributed among as many as 4 symmetry spaces. For centrosymmetric molecules, mutual exclusion rule exists. Third, it is possible to have silent normal modes that cannot be observed as fundamentals in IR or Raman. Next, totally symmetric normal modes are always Raman active and polarized. These may or may not be IR active. Unsymmetrical modes are Raman depolarized. And the last point, thus by noting polarization or depolarization of Raman bands, it is possible to say about the symmetry of the modes in question. Now, in earlier module, we have learned a method for finding the activity just by solving the various direct products and then taking the example whether it contains A1 or not. Now, that method or procedure is lengthy. Now, let us go for simple way of checking the activity of vibrational modes. The method of taking direct products and then evaluating, as we have discussed earlier, is time consuming. We can get the same result immediately just by looking at the character table. Take the vibrational mode, the activity of which is to be determined. See the character table of that point group to which the molecule belongs and look in the column. First, in front of the irreducible representations, whether there is a Tx, Ty, Tz or X, Y or Z as the basis for representation. If any of these bases is there, then the mode will be IR active. Otherwise, it will be inactive. For checking the Raman activity of a vibrational mode, see in the second, or you can say the last column, for basis function in the character table of the point group of the molecule. Whether there is any binary function of XYZ, that is XY, XZ, X square, etc. in front of that irreducible representation. If it is there, it will be Raman active. Otherwise, it will be Raman inactive. This gives a quickest way of finding the activity of vibrational mode. We will follow this procedure for classification of the vibrational mode. Which mode corresponds to stretching, which mode corresponds to angle deformation, and what are their symmetries type will be the discussion or further in this module. Now let us take classification of vibrational modes. In earlier modules, we have already discussed how to find IR and Raman activity of the vibrational modes, but we have said nothing about their origin, whether these belong to stretching of a bond or these belong to angle deformation in the molecule. Let us now find a method for getting this information. Classification of the vibrational mode using internal coordinates. It is useful to discuss analysis of vibrational modes in terms of stretching of bonds in between atoms and angle deformation. The internal coordinates can be of the type bond stretching, that is symmetric or antisymmetric stretching, angle deformation, rocking, wagging, scissoring, and twisting. In rocking, wagging, or twisting, the coordinates, the angles, and bond length within the group involved do not change. Rocking may be distinguished from wagging by the fact that the atoms in the group stay in the same plane. Some of these modes are shown in by figure as follows, and these are just I will explain with the help of the module as. Now let us take the water molecule, triatomic molecule. Now in this, if both these bonds, this bond and this bond, are stressed simultaneously, that is both are stressed simultaneously, or it will like this, stressed simultaneously, it is called symmetric. If we take antisymmetric, one of the bond is stretched and this is not stretched. This goes towards your oxygen, this goes from away oxygen. Again, this bond goes towards oxygen, or this hydrogen goes towards oxygen, and this hydrogen goes from your oxygen. That is, both these bonds, they are antisymmetric stretching, they are going antisymmetric. Now there is a in plane scissoring. If I am having this molecule and this is my bond angle, and both these bond, they can be squeezed like this or they can be increased like this. That is, it can be like this or like this. It is in plane scissoring. Then in plane rocking, that is the whole molecule, it can rock like this in the plane. This is my plane of the molecule over here, and it can rock in this manner in the plane. It remains in the plane and it goes under rocking. Then we have out of plane wagging. Just see, both of these, they go like this. Whole molecule, it wags like this. And then we have out of plane twisting. That is, one of these bond, it comes towards you and this bond comes towards me like this, just like twisting. That is, one of the bond is going is towards you, another comes towards me. It is just like twisting. So we are having these types of modes into these molecules. Now in the IR region, we will be considering only symmetric and antisymmetric bond stretching and then angle deformation, because the rest of them, they do not, this are not much responsible for your IR radiations. The most common internal coordinates are change in bond length, that is stretching, symmetric or antisymmetric. Angle deformation, that is scissoring, as I have shown you in triatomic water molecule, and we will now consider this. Only these will be used as basis for representation to get tau vibrations. that is stretching, or tau bending, that is angle deformation. To find symmetry spaces of tau stretch and tau bending reducible representation, these will be reduced to irreducible representation, and the results will then be correlated with those that were obtained using tau 3n method. That is, we have tau vibration is given by tau 3n minus tau t plus r method. Now, let us take the water molecule which belongs to C2B point group and again explain this method. The water molecule together with various symmetry elements is given in figure 2, and I will just also explain. Let us take this water molecule. This is water molecule. This is my YZ plane, that is the plane in which the molecule lies, and this is your XZ plane bisecting the angle, and this is my C2, this is my C2 axis, that is it can be rotated like this. So, in this molecule I am having a YZ plane in which the molecule lies, a XZ plane which is bisecting the HOH angle, and then a C2 axis like this which can rotate the molecule like this. Let us consider the various steps involved in finding this or in classifying these modes. First step is find reducible representation, tau bending or tau stretch, using two bond vectors as the basis. Find the number of unshifted bond vectors, then follow the following rules for finding chi which contributes towards tau. A vector which is unshifted by symmetry operation of the point group contributes chi r is equal to +1. A vector which is shifted to another position by symmetry operation of the point group contributes 0 to chi, that is chi r is equal to 0. A vector which is unshifted but only its direction is changed by the symmetry operation of the point group contributes chi r is equal to -1. Using character table of C2V point group, let us get irreducible representation, that is tau bending or tau stretching. First, let us find tau stretch, that is I will use two OH bond vectors as the basis. The symmetry operation C2 sigma xz and E and YZ, I will check the effect of these symmetry operation on both the OH bond, and the results are given in this table. Here what we see, the symmetry operation C2 and XZ interchanges both OH. Therefore, chi r is equal to 0. Under symmetry operation E and sigma YZ, symmetry operation both vectors are not changed. So, chi r is equal to +1. So, in this table we get tau stretch as 2, 0, 0, 2. And let us now reduce this tau stretch. And after taking this C2V character table, the reduction of this can be given as shown over here. Follow the standard reduction formula to reduce tau stretch. Since there are 4 operations in C2V point group, the order of the group is 4. The equation for calculations are A1 is equal to 1 by 4 within brackets 1 into 1 into 2 plus 1 into 1 into 0 plus 1 into 1 into 0 plus 1 into 1 into 2 is equal to 1 by 4 within bracket 4, that is 1. It means A1 mode is present only once. Let us check B1 similarly is given by 1 by 4 within bracket 1 into 1 into 2 plus 1 into -1 into 0 plus 1 into 1 into 0 plus 1 into -1 into 2, that is 1 by 4 into 0 is 0. it means B1 mode is not present. Let us go for A2 mode. 1 by 4 again within bracket, if we check it, it is again 0. It means A2 is not present. Let us check B2 mode is equal to 1 by 4 within bracket 1 into 1 into 2 plus 1 into minus 1 into 1, 0 is plus 1 into minus 1 into 0 plus 1 into 1 into 2 is equal to 1 by 4 within 4 is 1. It means B2 is present only once. Thus, tau stretch is equal to A1 plus B2. If we compare our result with tau vibration, that is tau 3n minus tau T plus R method, we have tau vibration is equal to 2A1 plus B2. Thus, we are short by A1 mode. How to account this A1 mode? Where from we will get this A1 mode? For this, we take double-headed arrow, that is HOH bond angle, as the basis for getting tau bending. Double-headed arrow is shown in the figure above. That is, if we take water molecule over here, the double-headed arrow will be over here. Here is the arrowhead, here is the arrowhead. It will be like this. So, I will just take this is the bond angle which is by double-headed arrow over here is shown. And I will see the effect of various symmetry operation of C2B point group, that is the effect of C2, E, sigma xz and yz. Now, how this double-head arrow behaves? Let us examine. Under E, this double-headed arrow remains as such, so it is plus 1 effect. Now, under the operation E, again I am writing plus 1. How? Now, this is my C2 axis. What happens? This double-headed arrow is not completely shifted, only half of the bond angle that is shifted into another half. If this is my C2 axis, it divides this bond angle, double-headed arrow, in two. So, it is not completely shifted, only one half of that goes into another half. So, it is plus 1 effect. Similarly, sigma xz, because one half of the angle goes into another half, so this is also gives me character plus 1. And sigma yz, the bond angle lies into this. So, we can say the overall effect of these operation E, C2, sigma xz and sigma yz on this double-headed arrow is 1, 1, 1, 1. And we can get the reduction for this. We get A1 is equal to 1 by 4, and by solving you will find it contains A1. And you try for others, that is A2, B1, B2, and you will find they will not be there into this. So, this double-headed arrow gives us the irreducible representation corresponding to A1. Therefore, tau internal coordinates is equal to, tau internal coordinates means I am using bond stretching and bond bending. So, tau internal coordinates is equal to tau stretch plus tau bending. Tau stretch is A1 plus B2 plus A1. It comes out to be 2A1 plus B2. The result is the same as we have obtained earlier using tau 3n as the basis for representation. Out of these three modes of water molecules, two modes A1 and B2 we have obtained by stretching, that is oxygen hydrogen bond stretchings, and one A1 mode is angle deformations. These modes of vibration are shown in the figure below, that is this A1 and B1. If I am taking these water molecules, if both these bonds they are stretched simultaneously, it is our A1 mode, symmetric. If one of the bond is stretched, that is if I stretch it like this and then it goes inside. So, it is called anti-symmetric stretch. So, in these stretching modes I am having one of them is symmetric stretch and another is asymmetric stretch, that is A1 mode OH bond angle increases. Now, in this final over here, that is the third scissoring bond deformation A1 mode HOH bond angle increases or decreases, in plane scissoring is there. So, we are having over here, that is OH bond either increases or decreases simultaneously like this. In another antisymmetric, one bond stretches, another decreases, that is one bond increases, another decreases. So, we are having these are the three symmetric, antisymmetric and angle deformation internal coordinates which are responsible for 2A1 plus B2 irreducible representation. Now, we have now classified the various modes, that this mode corresponds to which internal coordinates and which mode correspond to which internal modes. Now, if some frequencies are given, then how to assign this frequency? This will be our next part, to assigning of vibrational frequency to various modes. Let us again take actual IR and Raman spectra of water molecule. The tentative vibrational spectra of water molecule is given in table 1 below. Now, here the frequencies which are there, a slight difference in frequency is due to different media of recording of for the both of these two, and due to this these frequencies differs. Now, we have vibrational spectra and these are given in centimeter inverse. IR I am having 3657, 1595, 3756. Raman I am having 3657 polarized, 1595 polarized, 3756 depolarized. Before assigning these frequencies to be observed to the observed symmetry species of vibrational mode, following general observations are to be noted. These are based on large number of experimental data on large number of molecules and from chemical intuition. Number 1, stretching frequencies are higher than bending frequencies involving similar atoms. Symmetric frequencies are always Raman polarized. Since star stretch is A1 plus B2 and top bending is A1, it means bands at 3657 polarized centimeter inverse and 1595 polarized centimeter inverse, which is polarized in Raman, are of A1 type only, because these are the polarized, and one of these polarized A1 corresponds to stretching and another corresponds to bending. And since the higher frequency 3657 pol is due to symmetric OH stretching and lower frequency 1595 polarized centimeter inverse is due to HOH angle deformation. The third frequency at 3756, which is depolarized centimeter inverse, has B2 symmetry, that is associated with antisymmetric OH stretch. This antisymmetric OH stretch is near to symmetric stretch, that is 3657. Now, we can assign water frequencies of water molecules as follows. Symmetric OH, that is 3657 polarized centimeter inverse, and new one, it is polarized A1. HOH angle deformation 1595 polarized centimeter inverse nu 2, that is polarized A1. Antisymmetric OH stretch 3756 depolarized centimeter, that is nu3. Vibrational frequencies are generally written in decreasing order within each symmetry species and working further according to order of species given in character table. Here there are two symmetric frequencies, A1 type, totally symmetric species are considered first. In this spectrum, A1 mode at 3657 polarized centimeter is higher frequency, so therefore it is assigned as nu1, and next higher lower frequency belonging to A1 type is at 1595 polarized centimeter inverse, so it is assigned nu2. Next symmetry species which is not of A1 type is B2 type, which is not symmetric. Here there is only one frequency which is at 3756 depolarized, so it is assigned a nu3. This convention is generally followed all through. So like this we can assign nu1, nu2, nu3 to the various spectra of the water molecules. So in this module, what we have learned so far, we have considered again some general point about the selection rules of IR and Raman spectroscopies. We have also learned a direct way of checking the activities of fundamental modes, that is, either they are IR active or Raman active, just by noting the basis functions, the last two columns of the character table. Then simple method of classification of the vibrational modes in terms of internal coordinates, that is stretchings and angle deformations, has been discussed in detail. Detailed procedure for getting vibrational modes has been explained by taking the example of water molecules. Again further, the spectral frequencies for water molecules for both Raman and IR are given, and these spectral frequencies have been assigned as nu1, nu2 and nu3. And some general chemical rules were cited, that is, the stretching frequencies are higher than bending frequencies. Symmetric modes of vibration is always Raman polarized. By taking few of these points, we were able to assign the spectra of water molecule to the various internal coordinates, and we have given them, named them as nu1, nu2 and nu3.